So here we have a differential equation that models the growth rate of a population, and then we have a few questions to answer based on that. So the first question, we're looking for the carrying capacity of the population, and that's just going to be this number right here. So I will just put that down, 450. And then for the next question, we are looking for the size of the population when it is growing the fastest. So that's always going to be half of the carrying capacity. So half of 450 is going to give me 225. And then we're looking for the rate at which the population is growing when it is growing the fastest. Well, the dp dt right here models the growth rate of the population. And I'm interested in when it is growing the fastest, so I need to plug this in for p. So I'm going to get 0.004 times p, and I'll put this down in blue, times 450 minus p. And this right here is the answer to part C. And if this is an FRQ, you can just leave it right here. You don't have to simplify anything. But if you prefer, you could simplify this to 202.5, so I will put that down right here. And there were no units in this question, so you don't have to worry about putting down units for any of these. And now we will do part D, which is going to take up the most work, so I will erase this so we have room to do it. And we're looking to solve the differential equation, and we have the initial condition right here. So I will just write this down. dp dt equals 0.004 p times 450 minus p. First step, separation of variables. So I will multiply both sides by this, and I will divide both sides by this. So when I do that, I will get 1 over p times 450 minus p dp equals 0.004 dt. And now I can integrate both sides, so I will do that. And this integral is easy. This one, you have two choices. You can factor out a p from these and then bring things to the numerator and do a u substitution. But I will do that perhaps in a later video. I will just do this with the typical partial fractions. So the denominator is factored. These are my two factors, so I'm going to have one fraction over p and another fraction over 450 minus p. And then I have the dp right here equals integral of 0.004 dt. Alright, so I need to figure out what these numerators are going to be, so I'm going to do the cover-up method. So for this one, I'm going to have to set this factor equal to 0, so I have to use p equals 0, then I will cover it up and plug p equals 0 into the rest right here. So when I do that, I will get 1 over 450. That's going to be my numerator for the first fraction right here. It's going to be 1 over 450. Then for this one, I have to use this factor and set it equal to 0. So that means I need to use p equals 450. Then I will cover this one up and plug p equals 450 into these. And when I do that, I will get 1 over 450. So that will be my numerator right here. And now perhaps I will multiply the integrals on both sides by 450. That'll wipe these out, turn them into 1s. So I'll have the integral of 1 over p plus 1 over 450 minus p dp equals, when you multiply this by 450, you should get 1.8. And then the dt right here. And now we are ready to integrate these. So when you integrate this, you will get natural log of p. And then for this one, you'll get natural log of the denominator, and I'm not using absolute values here because growth rate is always positive. But be careful with this one because the derivative of this denominator is -1. So when you're doing the integral, you have to be sure to do the chain rule backwards. In other words, divide by that derivative. So dividing by -1, I'll just put down the negative right here. And this is going to be equal to 1.8 t, and I will put down the constant of integration on this side. Now, I just need to solve for p in terms of t, and also use my initial condition. So firstly, if I put these logarithms together, I will get the log of p over 450 minus p. And I'm not going to be able to do anything with that because I'll have the two terms in the denominator. So what I really want to do is kind of switch these two. So I'm going to multiply both sides by -1. When I do that, I will get natural log of 450 minus p minus the natural log of p equals negative 1.8t minus c. Now I have the difference of two natural logs over here. I can write that as the natural log of a quotient. So natural log of 450 minus p over p equals negative 1.8t minus c. And now I can exponentiate both sides, so I will just put down the e's right here. And here these will cancel out. And I'll be left with 450 minus p over p equals, I'm going to write this down as e to the negative c times e to the negative 1.8t. Let me make sure we have a decimal point right here. And now I can use my initial condition, which, if you recall, was p of 0 equals 75. So I will plug in 75 for p and 0 for t. So when I do that, I will get 450 minus 75 over 75 equals e to the negative c times e to the negative 1.8 times 0. Alright, then just simplify some things. This right here is going to give me 5, and then this right here is going to give me 1, so multiplying by 1 doesn't change anything. You can just cross that out, and we find out that e to the negative c equals 5. So I will substitute that right here. And on this side, I'm also going to split the fraction now, so I'm going to have 450 over p minus p over p, which is just 1, equals 5 times e to the negative 1.8t. Now I just need to isolate the p. I will add 1 on both sides. 450 over p equals 5e to the negative 1.8t plus 1. And I will do the reciprocal on both sides, so I get p over 450 equals 1 over 5e to the negative 1.8t plus 1. And I will multiply both sides by 450, and we find out that p equals 450 over 5e to the negative 1.8t plus 1.